previous part of the solution with the videos for this problem 3, we design for the deck of the sitting design. We consider bending, shear, and deflection. And now, because you're familiar with that, this process I'm not going to write down with this video. I just want to walk through the remaining solution for these problems. The next, after the sitting design, you design for the joints. What is that about? If you go back to this slide, you will see the joints and this one. So the previous sitting design, we determine space between the joints, and we select 24 inches joint spacings, and that basically between the joint you have here is 24 inches. And now go to the joint designs. So we assume, and the problem actually given, joints are continuous over 3 spans, so that we can use this table 13.5 to use the equation for bending, shear, and deflection. So let's go to that one, and this we need to determine the distributed load on the joints. How we determine? So the distributed load on the joints, it will be equal to joint spacing that determined in the sitting design, and then time the design load. And the joint spacing, we select 24 inches, so we convert that into feet. 24 divided by 12 inches per feet, time the design load that we have in the previous lesson videos, that is 130 pound per square foot. So you time that one, you can be able to determine the distributed load on the joints, and 260 pound per foot. So why that? Let me go here to explain, and that you can use the same reasoning for the following step. So the joints, and you can see between the joint is 24. So one joint, it will be carry 24 inches spacing. So 24, and you will time the distributed load, design load on the slab. Then you can be able to see the distributed load along the joints, and that's why we have that equation to determine here. So when you have the W, then you can go to this, and this is wood. Go to this table again. We can determine for bending. You can either use the first equation or the second equation. The first equation, I use that for the sitting, because we know the B, we select the width of the one bit is 1 foot, it means 12 inches. In this case, because that is the material for the joints is 2 by 8, so you can be able to determine the section modulus that you can use in this table, the section modulus with 2 by 8 in here, section modulus. So with that, you can be able to use the second equation as well, and that I think I'm going to use that equation that you can see there, and that equation section modulus. So you go to table 13.7, which is going down in your page number 7 of your final exam reference. So you can be able to find with the 2 by 8 inch nominal size of the joint, you can determine the section modulus, area moment of inertia, and of course the section areas. And with that, we can apply back to that equation, plug in. So the spacing needed, if we maintain the good bending, can stand with the allowable stress for bending, that will be maximum spacing is 87 inch. Similar for the shear, we can apply the same equation with the wood. So it will be 13.3 FVAW over W plus 2D, and that you have that here, and plug in with all the number you have FV, allowable stress for shear that the problem give us in here, allows both thread. For other member join and stringer FV 180. So and that the same for other properties. And like I say, if the problem don't give yes, you can go to the this table on page 6, page 4. You can be able to find out with different type of wood, the Douglas fir, California redwood, etc. So when you have that one, you can plug in that equation. You can find out for the share. So to ensure the share work 5, L maximum 114 inch. Deflection, the same. For deflection, go to that equation. And for deflection, the problem gives us the L over 360. So that equation you have, and that they give us E modulus I. We can find out from the table already determined W. So you can apply that. We can find out the L. And in this case, unlike the sitting, deflection govern in these scenarios, but for the choice, the bending is governed because that is smallest. 87, 114, and 107. So bending govern. So we choose the maximum stringer span is 87 inch. And make life easy, we select 84 inches. So it had to be less than that, 7 feet. Spacing that easy to get on site to 7 instead of 7 feet, instead of say 87. That difficult to remember, difficult to lay out. And when you have that, you can be able to continue with the same exactly process for design for stringer. So stringer design, we assume also continuous over 3 span. And distributed load again is going to be the stringer spacing time design load. For choice design, we just talked earlier, it will be choice spacing time design load. This similar equation. Stringer spacing, just previous equation, we have to select 7, so it will be 7 130, that is the design load. So it will be 910 power per foot. And go to table 13.7 with the cross section 4 by 8 inches. So go to table here, 4 by 8. You can be able to find out the area of the section modulus, and moment of inertia, and that you have that in A, S, and I. And apply the equation in third table 13.5, and with the wood, exactly the same stringer with the different properties. So we plug in, we find out for bending 71 inches, share 81.3, deflection 93.8. And again, the bending governs, and then the maximum source for span is 71 inches. So as you can see, if we go back to here, this is the process we have to design for sitting. We determine the space between the joints so that the bending work well for the sitting, share work well, and deflection work well. And then we go to design for the joint. We determine the spacing between the stringer, and for stringer, spacing between the joints. And then when we have that, the final step, we have to check for the short strength and check for crossing. Check short strength because we select short spacing. And in this case, the problem gives us the shore. Commercial 4,000 pounds of shore will be used. 4,000 shore. So that's the maximum load that they can carry, and that we need to check with that. So in here, shore in space, we have the load on the shore, and you can see in this table. So the shore here, the load on stringer is 910, the W, the distributed load on stringer is 910 pounds per square feet. So each shore, and you can see here, it will carry that load with the spacing, so that it will be, as you can see, 400 pounds. That is the shore spacing that we need. it determines the load. The maximum they can carry, the total load is 4,000 pounds. The distributed load on the stringer, it will be 910 pounds per foot. So with that, we can divide by that. We can, and unit conversion, we need the saw spacing is 52.7 inches to make sure that the saw can carry, because that saw is 4,000 pound allowable working load. So based on the strength desired for the stringer, the maximum saw span is 71 inches. For the load that the saw can carry itself, the maximum space between the saws is 52.7 inches. So the maximum saw span is the minimum of those two to make sure that the stringer work well and the saw itself also work well. So you get those two, and it will be 52.7, and make sure to round up, so select 48 inches. So saw spacing between this is 4 feet, and in this case the saw, the load of the saw cover, not the stringer. Stringer work fine because the space between the saw 71 inches, the stringer still work fine. But for the saw, because it only carry 4,000 pounds, then space have to be get closer, 52, as you can see there. So we select 48, and then check for crushing at the point where the joint rests on the stringer. So as you can see, the joint right on the stringer, it may have the local crushing in there. How can we do that? And that here that I show you here. So this is the black one stand for stringer, and the blue stand for joints, and the local, and you see cross section. Second one is just top view, and the crushing, the contact between the joints and the stringer. And how to determine that? As you can see, first we need to find out the load that the joint apply on the stringer at that local areas. So it equal to distributed load on the joint times the stringer spacing, because at one joint here, space, stringer spacing, that is the load distributed on the joint with the space, and that will be the equivalent load applied, concentrated load applied on that location, and same for this location. So you will have the 260 pounds per foot, that distributed load on the joints. The stringer spacing 84 inches that we designed earlier. Then, and that's what we choose. Then we divide by 12, it means unit conversion. So we have the concentrated load equivalently applied the joint on the stringer is 1820 pounds. With the bearing areas, as you can see here, equal to the width. One side is the width of the joints, and the joint is 2/8, and the actual side is 1.5 inches. The width of the stringer is the stringer size, nominal size is 4/8, then the actual size is for the width is 3.5 inches. For those of you not familiar, you can go back to the first video of this lesson. We determine all of that with the table in there. Here. Okay, so that you have the actual size from reference page 5 of the final exam reference. So when you have that one area, so you get, the load divided by the areas as determined in the reference that you have here. Compression, crossing, P over A, as you can see there. So that is P over A, 1820 divided by 525. So you get 347 PSIs. And that had to be less than the allowable compression perpendicular to grain, and that it gives us in the problems, as you can see here. And why we only need focus on grain? Because that one is much smaller than allowable stress for compression parallel to grain, A50. So in this case 504.5. So it already get the small one it work fine, then of course the parallel to grain it should be working fine. So we have to small it and compare. So have to be the actual have to be less than the allowable. So actual less than allowable. So okay. What if the actual is greater than? So we need to different way. You need to increase the area, so increase the width of the members, structure and choice, or to reduce the load. How to reduce the loss? You cannot reduce the load of the design load. You may reduce the spacing, so you can put the spacing between the structure closer. So that also a scenario. So that you can look beyond the problem to see with different scenario how can I apply that. And this close for problem 3 of this lesson.